Okay, I'm doing. Yeah, so only the front part will be recorded, and the closed session I will stop the recording. So that's not a worry. Okay, so we are all there, right? So you are all ready, right, Anagha?
Yeah, I'm ready.
Okay. Okay, so let me start the defense proceedings, Anagha's defense proceedings. So I normally say a few words to introduce the candidate, and so that's what I will do in the next couple of minutes. So Anagha Kulkarni received her bachelor's in computer science from Gogte Institute of Technology in Belgaum, which is also her hometown. She then received a master's in computer science from University of Southern California, and she joined ASU and our research group in 2015. Um, During her time at ASU, she made many important research contributions in the area of human-aware AI systems. She published multiple papers in premier conferences, and these papers have already received around 320 citations as of yesterday night. And she co-delivered a well-received tutorial at IIII 2020 in person, mind you. That was the last conference where we were all actually in person, again on human-aware AI. And she's currently co-authoring a monograph based on that tutorial and the work that we surveyed on human-aware AI. I believe we are shipping the first draft of that book this week. So she was, juggling all these things at the same time. And I think she also had fun going to MSR AI Breakthroughs workshop last fall. And she interned at Park and Facebook, Instagram. And pending successful completion of this defense, I believe she will be joining the AI group at Invite. So during her time at ASU, Anagha forged strong collaborations both within the lab, especially with Tathagata and Sharat, who she did the tutorial with, and she also went to the Microsoft Imagine-COPP with. And of course, with David Smith and Sarah Karen outside of ASU. Along with Tathagata, as I said, and Sharat, she went to the Imagine-COPP finals with some swanky tools for human-robot teaming. She also helped as the honorary TA multiple times for Intro to AI course, and she's a very conscientious TA. Within the lab, Anagha has increased our group diversity quite a bit, and I specifically mean the fact that she is the first Kannada PhD student coming out of our lab. We have most of the other languages, but Kannada is the first time, I guess. Seriously though, Anagha is known to be a fierce defender of gender equality and environmentalism, and her dislike for the coffee smell wafting through the lab air. And of course, not being afraid to hold people accountable when they strayed too far from the norms. She's known as the only one who could actually effectively push back on certain dictators such as Tathagata, when he was around. So we will be missing Anagha when she graduates. Actually, it's been last 1 year, we have been sort of only on Zoom. So hopefully we may not miss as much as we would have if it was a physical, the old times. But still, hopefully, she will do great after the defense, assuming that the defense goes well. Today itself, she will be talking about her thesis dissertation on synthesis of interpretable and obfuscatory behaviors in human-aware AI systems. Go ahead, Anagha.
Okay. Thank you, Rao, for this kind and thoughtful introduction. I would like to welcome everybody to my defense. And now I'll get started with my thesis topic, synthesis of interpretable and obfuscatory behaviors in human-aware AI systems. These days, AI systems have become part and parcel of our day-to-day lives. From an AI assistant in your living room, to a smart toothbrush in your bathroom, to a smart fridge in your kitchen, to a smart car in your garage. But not all of these AI systems are human aware. That is, not all of these AI systems take into account the human's mental model. For instance, an autonomous car that expects the human driver to be ready to take over the wheel in just a few seconds without taking into account the amount of time it takes her to react to a situation is not really human aware. And that is what this tweet by Rao points out after Tesla's one to many accidents. Therefore, it is quite crucial for AI systems to take the human's mental model into account. There are several human aware application domains. For instance, there are commercial settings like factory floors, warehouses, restaurants, etc., where humans and robots collaborate together and work alongside each other. Further, there are several decision support settings like helping pilots in a cockpit or doctors during surgery, where again human aware AI is important. But not all applications of human aware AI involve cooperative entities. Instead, there are some domains that also involve adversarial entities. For instance, you can think of mission planning or military planning scenarios where the adversary is tracking troop movements. Or more commonly, you can think of grocery stores and department stores where they place these Bluetooth beacons in the aisles to track the humans and their interests without taking into account the human's consent. Therefore, there are such domains where the AI systems need to model the observers in the environment, even if they are cooperative or adversarial. And then the AI systems need to behave in a way that conforms to these two types of entities. So now let's look at what my thesis focuses on. So essentially, my thesis focuses on synthesizing behaviors in human-aware AI systems to deal with cooperative as well as adversarial entities with implicit communication. So what this means is, for instance, a robot that is operating in the presence of a human, it has to take into account the human's mental model. So here you have an example of an urban search and rescue scenario where the robot's floor map is given here, and the robot's goal is to access this medkit. Now, as you can see, the human's mental model has a different floor map. And that this might be due to humans' partial or inaccurate understanding. And this might lead to a lot of differences between the robot's model and the human's mental model. When such differences arise, the robot has to take into account the human's mental model to make its behavior interpretable. And in other times, even if the human has correct understanding of the robot's task or environment, human may still suffer from noisy observations. Here in this example, as you can see, the floor map is the same, but the human here is using a sensor model, and this sensor model has noisy observations. Let's say the human has a GPS sensor which is not accurate within 10 feet, and therefore when the robot moves right, it is not clear to the human in what direction the robot has moved. Therefore, in such situations, the robot also has to take into account the human's perception limitations while synthesizing its behavior. So in general, when such model differences exist, the robot might want to communicate some information to the human. But then there are multiple ways of doing it, either explicitly communicating or implicitly communicating. But with explicit communication, there are multiple considerations that come into account. For example, the what, when, and how of communication. Further, explicit communication can suffer from vocabulary mismatch. For instance, the robot might give a technically cryptic message to the human, which might not mean much to the human, or it can suffer from inherent delays. For instance, in the case of the Mars rover, it takes about 22 minutes for a message to reach from Mars to Earth and back to Mars again. Further, in some scenarios like disaster response scenarios, explicit communication might not even be feasible. Therefore, in all such cases, the robot can implicitly communicate its information, and it can do so through its behavior itself. So now let's see what the robot can do. The implicit behavior that the robot can communicate depends on the type of entity that is present in the environment. For instance, if there is a cooperative entity in the environment, the robot needs to behave interpretably. Versus if there's an adversarial entity in the environment, the robot needs to behave in an obfuscatory way. Here, as you can see, the robot, by making this interpretable motion, is actually signaling to the observer that it is going towards this rightmost medkit. Versus here, in the adversarial scenario, the robot is taking this ambiguous path, thus keeping its goal hidden until the very end. And that is what the robot can do depending on the observers in the scenario. Further, in collaborative situations, we can also redesign the environment itself to make certain behaviors available to the robot and to improve the interpretability of the robot's behaviors. So in short, in the rest of this talk, I will focus on these broad behaviors: interpretable behavior and obfuscatory behavior. Under interpretable behavior, I will look at explicable behavior, which involves the robot executing behavior that conforms to the human's expectations. Then I will look at design for explicability, which involves leveraging environment design as a tool to improve the explicability of robots' behaviors. Then I will look at legible behaviors. Here, I will talk about plan legible and goal legible behaviors, which allow the robot to convey information about its plans and goals to a cooperative observer. Then I will talk about obfuscatory behaviors. This involves goal obfuscatory behavior, plan obfuscatory behavior, and secure goal obfuscatory behavior. Here, through its observation sequence, the robot will be able to hide information about its goals and plans. And further, in cases where there are adversaries that can query the algorithm multiple times with different inputs, the robot can also make the its behavior secure. Then I will talk about a more general scenario, which involves both adversarial as well as cooperative entities. In this case, the robot will have to balance the amount of obfuscation it provides versus the amount of legibility it provides the cooperative observers. And then finally, I will talk about assistive behavior. This was the work that I proposed to do last year. So this is what the rest of the talk will look like. Now let's get into explicable behavior. So as I said before, the robot's model and the human's mental model can diverge in multiple different ways. And when that happens, the robot's optimal behavior will no longer be explicable to the human in the loop. In fact, seeing an inexplicable behavior can lead to loss of trust, or can lead to loss of productivity, or in worst case can lead to dangerous situations around a physical robot. Therefore, the robot has to take into account the human's mental model and generate a behavior that conforms to this mental model and the human's expectations. Therefore, explicable plan is a robot plan that not only minimizes the plan cost, but also minimizes the distance between the robot's plan as well as the human's expected plan. So for this, we will see two approaches to solve explicable planning problems. First is model-based, and later we will look at model-free. In the model-based version, the robot has access to the human's mental model. There are several domains in which there is clear structure in the domains and there is clear expectation of how a task should be performed. In such domains, it is easy to retrieve these approximate human mental models and then allow the robot to use them. But the robot cannot plan directly with the human mental model. And this is because the human mental model may entail plans that are infeasible or prohibitively expensive for the robot to execute in the environment. And therefore, at best, this human mental model can serve as a guide for the robot to compute explicable plans. Therefore, explicable plan is a valid robot plan that is close to the human's expected plan. This essentially involves minimizing distance with the set of humans' expected plans. Therefore, the explicable planning problem is a tuple that involves the robot's model, the human's mental model, and the distance function. So let's see how this distance function works. So here we'll look at a example here in the autonomous car domain. Here you can see three plans, and these plans are plans of a car. So here in the first plan, the car shows a left indicator and moves to the left lane. In the second plan, the car gauges the traffic flow and moves to the left lane. While in the third plan, the car shows right indicator and then moves to the left lane. As you can see, the first plan is fully explicable, but the last plan is fully inexplicable, and the middle plan is somewhere in between. So different plans can range from fully explicable to completely inexplicable spectrum. And although these plans are all mostly similar, they just differ in one action, that is the first action. And therefore, we cannot use simple syntactic distance functions which just look at action distances and so forth. And therefore, we need a more complex distance function to capture the explicability distance. And therefore, we'll be learning an approximation of this using some combination of plan distances. So this is how the approach looks. Approach for generating explicable plans. So first, we collect a set of candidate robot plans, and these candidate robot plans have a varied amount of explicability. And then we collect a set of expected plans from the human's mental model. And then we use plan distances to capture the distances between these sets. And then using test subjects, we collect explicability score values for each of the candidate robot plans. Our goal here is to map the plan distances to the scoring scheme that the humans use in rating the plans, rating the robot plans. We want to learn this scoring scheme in terms of the plan distances. And then once we have this learned model, we can use it as a guide to make our search generate explicable plans. We performed a bunch of experiments on our approach. Specifically, we performed experiments in autonomous car domain and delivery domain. And as you can see here, these two graphs show the explicability scores for the plans tested in these two domains. We queried the test subjects to check the explicability scores of our plans versus the optimal plans. And the plans produced by our planner had much higher explicability score. Further, you can see here, this is the plan cost. There are certain explicable plans that have the same cost as the optimal plans, but a planner that is not sensitive to explicability score may not really generate them. Now, let's look at another approach, model-free explicable planning. So here, in this approach, the human's mental model is not available upfront to the robot. So, like I said before, the explicable plan is essentially minimizing the robot cost as well as minimizing the distance between the robot's plan and the expected plan of the human. But since we don't have the human mental model, we don't have access to this expected plan. And so instead, we decompose this distance function into a function that takes a set of task labels as input. Now, these task labels could be labels for tasks that can be performed in the environment, say building a block tower or collecting some items, etc. And then a labeling function. This labeling function labels each and every action in the plan. Here we hypothesize that if an action can be associated with one of the task labels, then that action is an explicable action. But if an action cannot be associated with any of the task labels, then that action is an inexplicable action. And then we use a conditional random field to learn this underlying pattern that characterizes explicable behaviors. Here is a demo of how the explicable behavior is generated. So on left, you have this robot here whose goal is to build a tower of height 3. And on the left, you have a block that the robot can, and on right, you have 2 blocks. So to build a tower of height 3, you would expect the robot to put this block on top of the other 2 blocks. But if you see the robot perform its behavior, you see that the robot does it the other way around. And that is because this block here, purple block, is slightly heavier for the robot, and therefore that plan is an expensive plan. But after training the robot with the explicability model, you can see that the robot can find a plan that conforms with the human's expectations. So we performed a bunch of user studies in this block stacking domain, and then we found that the 97 in comparison to the optimal planner, 97% of the actions in all the plans had high explicability, had a explicability label, versus optimal plans which didn't have that many explicability labels. So now let's look at how we can leverage environment design to improve explicability. So the environment sometimes might not be conducive to explicable behavior, as we've seen before, because the environment can lead to either infeasible or prohibitively expensive plans. Let's look at this example that we have here. The robot is operating in this restaurant domain, and there are 2 dining tables that are separated by some distance. The tables are actually close enough such that the robot cannot really move in between these 2 tables. But in the human's mental model, this is not quite apparent to the human. And the human thinks that the robot can actually pass in between these 2 tables. And therefore, the human expects the robot to perform a plan that is not even feasible in the environment. But in highly structured settings like, say, factory floors or restaurants, we can actually redesign the environment to boost certain types of explicable behaviors. And redesigning environment basically allows us to maximize or minimize certain objective for the robot. Environment design itself has pros and cons. Environment design can lead to permanent or semi-permanent modifications in the environment. These might be associated with one-time but possibly expensive design cost. But on the other hand, environment design might make much more sense when a certain task is being repeatedly performed in the environment and the environment is optimized for that task. So therefore, in this work, we will focus on the problem of facilitating explicable behaviors when the robot is performing a set of tasks in the environment, and these tasks are being repeatedly performed over a horizon. We will explore a way to balance the trade-off between this one-time but possibly expensive design cost and the repetitive cost that the robot undergoes to make sure that its behavior is explicable every time. So essentially, we will look at this problem of environment design for a single task, and then we will extend it to the problem of environment design when there are multiple tasks available in the environment and the tasks are being performed over a horizon. We will also look at explicability in definition in this longitudinal setting. So this is the running example that I'll be using throughout the discussion here. This is a restaurant scenario, and the robot here is serving this booth G1, and it ends up going back and forth between kitchen and the booth. Since these two dining tables are close by to each other, the robot cannot really take this path in between, but the human actually expects the robot to take that shorter path. So when there is a single task in the environment, this basically involves, say in our example, serving a new customer at a booth only once. So with respect to such a setting, we want to find an environment that maximizes explicability. So in essence, we want to find an environment that satisfies this following objective of minimizing the minimum inexplicability score, that is maximizing explicability, further minimizing design cost, and also minimizing the planned cost that the robot undergoes to behave explicably. And a way to do that is as follows. This essentially involves searching over the space of valid environment configurations. And our algorithm consists of these two loops. In the outer loop, we essentially go over all possible environment configurations. As you can see, this environment here is the initial environment in which the robot was operating. And then we can apply some design modifications like moving the serving tables or moving the dining tables, etc. And that will lead to new environments. And then in each of these environments, we will perform a search to find a minimum inexplicability plan, minimum inexplicable plan, that is the most explicable plan. And we can reduce this problem to a planning problem. And in this compiled problem, an action is executable by the robot if and only if its preconditions are satisfied in both the robot's model as well as the human's mental model. And it produces effects consistent with both the models. And once we have that, then we will find an environment which optimizes our objective function. So this is the example that we had for the single task, where the robot took this roundabout path and then the human expected robot to take this path in between. So then once we run our algorithm, we find that by pushing these two serving tables behind, the robot can actually take this roundabout path now, and thus makes the robot's behavior explicable to the human. Now let's extend this setup to a setting where we have multiple tasks in the environment, and also these multiple tasks are being executed over a time horizon. So basically, at each time step, the robot performs a task given by the probability of the distribution over these tasks. And essentially, so far we have looked at explicable behavior in a one-time interaction setting. But now we'll be looking at explicable behavior in a multi-interaction setting. And that has a longitudinal impact on explicable behavior. This is because the human's expectations could evolve. For instance, consider a scenario where you see a robot doing something inexplicable once. When it's doing it inexplicable once, you're surprised. But if you see the same behavior over and over, then you tend to think this is how the robot works, and you tend to ignore the robot's inexplicability. And that is what we try to capture here using a discounted Markov reward process. So basically 1 by gamma times the human thinks that the human ignores the robot's inexplicability, and that leads to a reward of 0 to the robot, versus gamma times probability of performing that task. The human does not ignore the inexplicability, and that leads to a reward of the inexplicability score of that task. So then that in this setting now, our task becomes the robot is serving either of the two booths with a probability given by the distribution over the tasks over a time horizon. And now our objective function gets modified as follows. Here we are now looking for expectation over the minimum inexplicability score given the human's tolerance to inexplicable behavior. The design cost remains the same as before. And the expectation over plan, and for the plan cost, we now again take expectation over the plan cost for each task given the horizon. So this is the modified setup. Here there are two tasks being performed over a time horizon, and again the human expects the robot to take this path in between, but then the robot takes this roundabout path. After doing the design, that becomes explicable to the human. We performed a bunch of empirical evaluations for this approach using IPC domains. And the way we set up the domains for explicability as well as for environment design, the details of that can be found in the paper. We show here that the inexplicability score in fact decreases significantly after the design is uh, modified in the environment. We also show that there is some interplay that happens between the size of the design cost and the time horizon as the time horizon increases. Now, let's look at legible behavior. So as we saw in the previous setting, there can be multiple different tasks that the robot can perform in a given environment. And when there are multiple tasks, the human may not have an idea of what task the robot is actually performing currently in the environment. And in such cases, the robot can implicitly communicate this information to the human by performing either goal legible behavior or plan legible behavior. So goal legible behavior allows the robot to convey its goals to the human observer, and plan legible behavior allows the robot to convey its choice of actions to the human observer. So let's look at the problem setting here. So here we have a robot that can perform deterministic actions in the environment and has full observability of its activities, versus an observer who receives observations from its sensor model and has partial observability of the robot's activities. So this essentially becomes like a scenario like this, where the human has the same floor map, but has this noisy sensor model, which stops the human from understanding in what direction the robot has moved. That's because the noisy sensor model that the human has is not accurate, say within 10 feet or something. So in such cases, the robot can take into account the perception limitations that the human observer has, and then it can generate observations that put the observer in a desired belief state. We call this controlled observability planning problem, COPP in short. Now let's look at the goal legibility and plan legibility problems. So these problems are problem variants of this COPP framework. So first, let's look at goal legibility. In goal legibility, the problem is that the robot has a set of candidate goals. The human is aware of this set of candidate goals, but does not know which of these candidate goals is the robot's current goal. And therefore, the objective of the robot is to limit the set of possible goals in the observer's belief to at most J goals, thus making its behavior J legible. Let's see an example here. So here we have this scenario where again the human has a noisy sensor model and cannot tell in what direction the robot is moving. And in this setup, the robot has this task of performing a survey room survey room task, as well as treating one of the victims in this on this floor. Now, if the robot does the survey task first, then it is at an equidistant point from both the victims. And at that point, it is not clear to the human which victim did the robot treat. But on the other hand, if the robot first treats one of the victims, as you can see, both the victims are at different lengths from the robot, and that would reveal to the human um, which victim was treated, and then the robot can do the survey task. Thus, the robot has made its behavior legible with respect to its goal in this setting. So to solve this, we will use a general algorithm template that will be useful for solving any of the COPP problem variants, that is both goal legibility, plan legibility, etc. So first, this solution approach takes the COPP problem as input, and the output is the observation sequence and the solution plan. In this algorithm, there are two loops. In the inner loop, we run a standard heuristic guided forward search, in which we update the observations and the belief updates that the observer goes through. And then the goal test and the heuristic function are customized for each problem separately. And the outer loop increments a state duplication parameter delta, and this parameter increments at each iteration and allows for systematic exploration of multiple paths to a state. So now let's look at how we can modify the goal test and the heuristic function to suit the needs of goal legibility. So in goal legibility, we want to make at most J goals possible. So that is, at least n minus J goals should be absent from the belief, from the last belief. That's the goal test. And in the heuristic function, we not only minimize the cost to the true goal, but we also maximize cost to these n minus J goals that we want to be absent. So here is a demo of a goal legible scenario. So this is like a household scenario where the robot is actually preparing a meal for the human, and it wants to communicate what ingredients it will be adding. So it asks the human to pass the can of sugar, thus revealing to the human what ingredients it will be adding. Now let's look at plan legibility. So plan legibility is again part of the same COPP framework. And here the robot has a single goal. So the human is aware of the robot's goal, but the human is still trying to infer the actions that the robot will perform to achieve that goal. And to do that, to make this legible, the robot can generate an observation sequence that is consistent with at least m similar plans, such that these plans are at most d distance away, thus making it easier for the human to guess the possible actions in that plan. Let's see with an example here. So here we have a scenario, again the similar scenario where the human has a noisy sensor model, and there are two medkits that the robot can take. So basically the robot's goal is to take one of the medkits and treat the victim. Now if the robot chooses this leftmost medkit, there are many 4-step plans that lead to this medkit, and further two two-step plans that lead to the victim. On the other hand, if the robot chooses this other medkit, there are only two two-step plans and one two-step plan to the victim. So this observation sequence produces more similar plans than this one. And that is what we want to do. This will allow the human to guess some of the actions that the robot will be performing. To solve this, we will then again modify the goal test and the heuristic function in that algorithm. And here, the goal test ensures that at least M plans are reaching the goal. The heuristic function, apart from minimizing the cost to the goal itself, also makes sure that the maximum distance between these belief plans is minimized. Now, let's look at some of the obfuscatory behaviors that the robot can perform. So, an AI system that is operating in an adversarial environment needs to make its sensitive information safe. It needs to be able to minimize the information leakage of its internal information. And that's where the robot can use goal obfuscatory, secure goal obfuscatory, and plan obfuscatory behaviors. Goal obfuscatory behavior allows the robot to hide its true goal from an adversary, while plan obfuscatory behavior allows the robot to hide its choice of actions from the adversary. Secure goal obfuscation allows the robot to maintain goal obfuscation even when the adversary has access to the algorithm and can query that algorithm with multiple different inputs. We will see in a bit what this involves. So all these three behaviors again are part of the same COPP framework, and the goal obfuscation problem is as follows. Here, the robot has a set of candidate goals, inclusive of its true goal, and it wants to hide its true goal from the adversary. The adversary has access to the candidate goal set, but is not aware of the robot's true goal. So here, what the robot can do is it can increase the possible goals in its belief by making its belief have at least k goals. The robot can make the behavior k ambiguous, thus keeping its true goal hidden. So to solve this, we will again have to modify the goal test and the heuristic function. So in the goal test, we ensure that at least k different goals are possible in the observer's final belief. And in the heuristic function, we not only minimize the cost to the true goal, but we also minimize the heuristic cost to the k-1 goals. So here's a demo of a goal obfuscatory scenario. So here the robot is working on some secret recipe and doesn't want the human to find out the ingredients that are being added, and therefore distracts the human into doing some other work. And when the human is inattentive, then it performs the actions, thus obfuscating the ingredients. Now let's look at secure goal obfuscation. So basically, the previous approach that we saw can not keep the goal obfuscation secure when the adversary has access to the algorithm, and the adversary can run the algorithm with multiple different inputs. When this happens, the observer will know what was the goal that the algorithm was run with, and it will reveal the true goal to the observer. But to avoid that, what we can instead do is we can choose a random set of k goals that is inclusive of the true goal, and then pick one of the k goals as the random true goal, and then compute a plan to this random true goal. And then using the observation sequence to that, we can reconstruct the path to the actual true goal. So this, even though it reveals to the observer what was the actual goal that the algorithm was run with, it still maintains the goal obfuscation. It still keeps the true goal hidden. So now let's look at plan obfuscation. So plan obfuscation is the opposite scenario of plan legibility. Here, the robot has a single goal, and the adversary is aware of that goal, but the adversary is not aware of what plan the robot will use to actually achieve that goal. And here the robot can use an L-diverse plan such that its observation sequence is consistent with at least L plans that are at least D distance away. So here our goal is to, so again we can modify the goal test and the heuristic function here. And for the goal test, we have to make sure at least L plans are reaching the goal. While in the heuristic function, we want to maximize the distance between the belief plans. So here we not only minimize the cost to the goal, but we also maximize the minimum distance between the possible belief plans. So I was also part of a survey that established a taxonomy over different robot behaviors. Earlier in the literature, there were multiple terms that were being used to refer to same behaviors. So this survey established a hierarchy and taxonomy over these different behaviors and categorized them into a coherent taxonomy. So now that we have seen both legible and obfuscatory behaviors, now let's look at a more general setting, which involves both adversarial observers as well as cooperative observers. So this is like a more generalized version of the COPP framework. We call this mixed observer controlled observability planning problem, that is MO-COPP. And here the robot has to balance the amount of obfuscation it uses for its adversaries with the amount of legibility it wants to convey, that is the information it wants to convey to the cooperative entities. And this setting is similar to the COPP setting, except that now it has two different observers, one a cooperative, the other an adversarial. And both of these observers have different sensor models. The robot, who is aware of the perception limitations of both of these observers, uses these different sensor models to convey information to the cooperative observer while simultaneously obfuscating information from the other observer, that is the adversarial observer. Let's see with an example how this works. So here we have a truck agent whose goal is to deliver two of these packages from either of the factories to the delivery area. And we have two observers in the environment, a cooperative observer and an adversarial observer. The cooperative observer has two types of observations. That is, the cooperative observer can identify which factory the package came from. You can think of this as the cooperative observer has some prior communication with the actor and therefore has access to a database that allows it to recognize between packages of factory A versus packages of factory B. Versus observer X, who does not have any such prior communication, has only one type of observation. That is, it cannot tell which factory did the package come from. So here we can look at a plan, this plan 1, which involves the actor taking a package from factory A and one from factory B. So for the observer C, this leads to 4 different states in its belief. Whereas for observer X, that is the adversarial observer, there are much more options. That is, there are 6 in total options that exist in its belief state. Now, let's look at another plan. Here, the observer, instead of taking the packages from 2 different factories, takes the packages from a single factory. What this results in is that the observer C can now differentiate between what the robot is actually doing and has a single state in its belief, versus the observer X still has all possible options in its belief. And this plan essentially maximizes the amount of goal legibility to one observer while maximizing the amount of goal obfuscation to the other. And that is what we want the MO-COPP solutions to do. Therefore, we established this goal difference metric. This goal difference metric essentially encapsulates the idea that there is this balance between amount of goal obfuscation and amount of goal legibility. For instance, let's say there are n candidate goals, then the best possible obfuscation would involve all n goals, versus in the case of legibility, the best possible legibility scenario will only involve one goal. And that is what this goal distance metric tries to capture. So when we evaluate both of the plans that we saw in the previous example, then we see that the goal distance metric for plan 1 is 0.4, while that for plan 2 is 1. And that is the kind of plan we want, which maximizes goal obfuscation as well as goal legibility for the two observers. And so we tried two different solution approaches to solve this problem. First, we looked at an IP encoding, which solved the problem as a constraint optimization problem. The details of this encoding can be found in the paper. And then we also used the algorithm that we saw before for COPP. We used it and extended it to suit the needs of this MO-COPP problem. And then we performed a bunch of evaluations to see the strengths, to see the relative strengths of these two approaches. The IP approach produces better quality solutions since it produces optimal solutions, whereas the search only produces satisfying solutions. Therefore, for GD metric, IP produces higher scores. Versus this search approach is a much faster approach and can handle more complex problems in comparison to the IP approach. So now let's move to the final part, that is the assistive behavior. So in this setting, the robot is trying to assist the human who has a task to solve in the environment. Here, the robot's goal is to provide proactive assistance to the human. The thing with proactive assistance is that the human may not be expecting to be helped, and therefore it makes proactive assistance challenging. Further, in some environments, the human may not even may have only partial observability of the robot's activities. For instance, if the human and robot are operating in the same environment, the actions done by the robot in another room will be hidden from the human. And in such cases, proactive assistance becomes even more challenging. And therefore, the robot has to control the human's observability to communicate this potential assistance that it is providing to the human, so that the human realizes this cost reduction that the robot's assistance provides. Therefore, proactive assistance should not only be provided, but should also be seen to be provided. Now, let's look at this example here. We have a scenario where this red dot represents the human in the environment, and the human's goal is to find a medkit in one of the rooms and to treat a victim in room E. Now, the human does not know which of these rooms actually contain the medkit. The robot, on the other hand, who has been working on this floor for quite some time, knows the locations of these items in all the rooms. And therefore, it goes in one of the rooms, takes a wagon, brings the medkit, and then displays that the wagon actually has the medkit to the human, and then goes and places it in room E. Now, if the robot had not shown the human that the medkit was present in the wagon, the human would have never known that the medkit is there, and the human would still go looking for the medkit. So it's very important for the robot to actually make sure that the human is aware of the assistance that is being provided. Now we'll look at a bunch of guidelines that will help the robot be a proactive assistant. First of all, the robot should only assist the human when it is sure that it can reduce the human's optimal cost. Further, the robot should, whenever the robot assists, it should make sure that the human is aware of this potential reduction in her cost. And further, the robot should provide the best possible help that is possible in the environment. That is, it should optimize the overall human's cost of participation. Now let's look at the problem setting. Again, we have a similar setting here. The robot performs deterministic actions and has full observability of its activities, but the human now has a goal of her own and receives partial observations of the actors of the robot's activities through her sensor model. So essentially, since the robot wants to proactively assist and the human has partial observability, the robot has to control the human's observability of its actions by making certain parts of the state legible and thus revealing some information to the human, and also obfuscating some other parts of the state by hiding some unnecessary complexities from the human, thus allowing the human to realize the reduction in her cost. So now let's see how these guidelines can be formulated. So the first guideline stated that there should be reduction in the human's cost. So this term here implies the optimal cost that the human will face if there is no interference from the robot. And this is the cost that the human will face if the human actually participates in the robot's plan of assistance. That is, acts after the robot has performed assistance, and therefore this cost differential should be less than zero for the human. That is, there should be a reduction in the human's cost when it participates in the plan. Further, human should be aware of this potential reduction. So as the robot is acting in the environment, the human is updating her belief in her mental model, and the final belief that the human ends up in should also result in a cost reduction that is equal to the reduction of the cost differential from the first guideline. So this allows the human to become aware of the potential reduction in her mental model. Then finally, the robot has to optimize the overall plan cost. That is, the robot should provide the best possible help and should take into account the amount of work that the human puts in solving the rest of the plan, as well as the amount of work the human puts in observing the robot. So because the solution space now becomes like a constrained space, we look at Monte Carlo tree search to perform to sample quickly some assistive strategies. So we build a utility tree that allows us to look at these belief states that have high utility value. And for that, we do the following. So this is how the typical Monte Carlo tree search works. It has 4 phases: selection, in which the tree is grown, expansion, and then simulation of one of the nodes. And then if the node reaches the goal, then back propagation of the reward or the penalty. So we do the selection using UCB1 algorithm. And in the simulation phase, we use conformant planner to simulate the human's plan. So basically, the robot reaches a belief state, and then the simulation runs what the human would do in that state. If the human can actually solve, given the belief state, solve her task efficiently, then that reward is back propagated. So once we have this utility tree which has sampled all assistive plans, we can then do a search over this tree to find the best possible assistive plan in this scenario. We performed a bunch of evaluations. We did user studies as well as empirical evaluations. In the user studies, we show that in the baseline algorithms did not take into account the fact that the human needs to become aware of the potential assistance, versus these two grouped bars here reveal are for the proactive assistant. And as you can see in the baseline, the test subjects thought that the robot was only working on its own objective, versus in the um, proactive assistant case, they were aware that the robot was actually working to help them. And that's what this red bar here shows. We also performed empirical analysis, and we saw a steep percentage decrease in the human's cost when the human participated in the proactive plan. That is, the human acted after it was aware of the proactive assistance. So that brings me to the summary of my talk. So in short, whenever the robot acts in the presence of any observers, it should reason with their mental models. And if the observers have perception limitations, it should also take those into account. In cooperative environments, unless the robot wants to communicate, it should always act explicably. That is, it should conform to the human's expectations. Further, if it wants to communicate some information, it should use goal legible or plan legible behaviors to communicate information about its goals and plans. Further, if it wants to assist a human, it should ensure that the human is aware of the potential reduction in her cost. And also, in cooperative environments, we can redesign the environment itself to facilitate certain behaviors and to improve the interpretability of those behaviors. Further, in adversarial environments, the robot should be able to hide information from adversarial entities. It can do so by behaving in goal obfuscatory and plan obfuscatory ways. The robot's goal obfuscation can be made secure to adversaries who can query the algorithm with multiple different inputs. And in mixed environments where there are both adversarial as well as cooperative entities, the robot should be able to balance the amount of information it shares with the teammates with the amount of information it hides from the adversaries. So with that, I'd like to point you to the list of my publications. And yeah, like Rao mentioned, parts of this tutorial did appear in, parts of this talk did appear in the tutorial that we did in AAAI before the pandemic. And yeah, with that, I'd like to open the floor to questions. Thank you.
Okay, so thank you, Anagha. So right now, the floor is open for questions from anybody, including the committee members. And then after the open period is over, we will essentially shift to a closed session where only the committee members will talk to the candidate, Anagha. So right now, anybody who would like to ask a question, including the committee members, feel free to do so. And you can, if you are one of the non-committee members, just unmute yourself and ask.
Hey, Anagha.
Hey.
You know I was going to be the first loud one, so let me start.
Sure, go ahead.
So when generating legible behavior, you speak of how the robot has to work with the mental models of the human in the environment in order to act legibly. Has there been any thought given to how this scales or changes when you have more than one human and differing mental models? Because I imagine the problem can get hairy very quickly.
Right. So the formulation that I have in my MO-COPP work, that can be actually extended to a situation where there are multiple different cooperative observers and they have like different sensor models and different mental models. So that encoding itself can be like easily like extended to that. And also even in the search approach, you can have like different belief states that you maintain for each of the different cooperative observers that you have, and then like try to find a solution that still meets your constraints.
Thank you.
Yeah.
Other questions?
I had one. I was curious, when you said you've done a lot of user studies on sort of like goals and the explicability of the goals. Did you see like a difference between certain types of goals and how easy or how legible certain are?
So I think that would depend on the domain itself. So the kind of, in the experiments that we did, the goals were more or less similar. So in the block stacking thing, the goals were like to build towers of different lengths. Then in the autonomous domain, the goals were like changing lanes and like taking turns. Like at a four-way stop. So they were like kind of similar to each other. So, but I assume if the goals are very different, then maybe the model that is learning the underlying behaviors will like suffer from that diversity of goals.
Okay.
Other questions?
Got a couple of detail questions before I get to the juicy ones. Back on slide 21, could you pull that up?
Yeah. Yeah, this one.
Yeah, that's it. I'm curious about how you actually do the search here.
Okay.
You refer to this as reconciliation search, and in general, it's difficult to fold an optimization function back into the search in a meaningful way that gives you good search guidance. And so I'm curious as to how you do that.
So the thing was here, this distance function that was learned took like plan distance measures and then mapped it to an explicability score for that domain. And then while doing the reconciliation search itself, what I did was at each step, I would compare the plan prefix that is being done with the plan prefix in the human's mental model. And these two plan prefixes were then, again, the plan distances are being computed for these two plan prefixes. And then that is mapped, like the regression model that is used gives the explicability score associated with those distances. And then according to that, you guide the search towards wherever it has higher explicability score.
I see. So as this forward state space search is going on, before you get to a complete plan, you're actually measuring each partial plan in the users. Okay. Okay, now can that mislead you at all, right? So if you see a discrepancy early, right, between the two models, but you know the rest of it.
Yeah, so that has some pitfalls. Like for instance, what if like the explicability could be like with respect to the entire length of the plan, and the explicability score itself can be changing. Like for the prefix itself might be fully explicable, but then you do something that's like inexplicable, or you do something that is inexplicable in the beginning and then later it becomes explicable. So those are the kind of cases that can become problematic in such approaches.
Okay. A couple of slides later, slide 24, I think it was.
Is it this one? Yeah, this one. Yeah.
Yeah. So here, you're doing this measure entirely based on just the actions, right? There's no measure of the actual causal structure being used here in terms of.
So the prefix, so whenever the human is labeling these actions at each time step, the human has access to the prefix and the goal. And then the human is like, okay, having done this, can I associate a label to this action right now? If yes, then yes, it is an explicable action in that context. If not, then yeah, it's an inexplicable action.
Okay, so the order of the actions is actually going to make a difference here.
Yeah, yeah. So these labels are being collected from like test subjects. So they are like looking at the plan and then labeling it.
Okay. All right, let me let somebody else ask questions if they want to before I get to juicy stuff.
I'll ask a few questions.
Sure.
I think in thinking about explicability, there are different reasons why we want explicability, and the costs could also vary depending on why we want explicability. Coming back to your restaurant example, right? One reason could be that the person will get surprised when the robot does not go in front of her and passes the other way. And there, the cost is just this kind of, oh, I don't understand what this robot is doing, why this robot is not going this way. Versus in a real collaborative setting, the human may be taking actions under the assumption that the robot will be going that way. And the collaborative plan may actually fail because of this inexplicability. So one question is, I know that you have a factor in your optimization where you can scale up or down, how important this is. But in reality, how would you quantify the different reasons for why we want explicability in practice?
Yeah, so the point that you made about like inexplicable behavior being like throwing people off track, like especially in collaborative scenarios, yes, that is definitely a thing. Like it can lead to, in the real situations, it can also cause accidents. So there are different things that you need to take into account. So here, when we talked about the inexplicability score, we actually, I think I have it here. We actually considered distance in terms of just cost-based distance. And so the cost-based distance just took into account the fact that, okay, this optimal cost is of length or of cost 4, and then this other plan is of cost 5, and so that distance. So we didn't really look at like a more complex distance functions, and that was the thing with like something like this. Like the idea was to capture more complex distances with like the first work, because like I said in that example, like these all things just differ in terms, they have the same cost actually. If you just look at cost distance, this wouldn't even like come into picture, or maybe it will come into picture, like maybe each action has different cost, but in terms of like say action distance or something, it might not be taken into account. So that's a really like central question, like how do you design this distance functions that can like actually correctly capture explicability score. And so you would have to like learn it only in one way or other, and that's what we tried to do here. We tried to learn it using the explicability scoring scheme, as well as in the other one as well.
I think learning it this way is a general approach that I think could work well in practice. However, the more formal approach could also be having a model of the human in terms of that human's intentions, goals, and plans, and querying that human model as you are inferring this cost. And I see that you are kind of moving in that direction at the last part of your talk, where that human plans are coming in. And you know, just in the future, I think there are ways to think about how the earlier parts of your dissertation could also benefit from thinking about how having access to the human model could address some of the issues about learning here. Just a thought on that. The second is when you talk about learning plan distances, it might be difficult for the human to provide the kind of labels you're assuming. And I think David is getting into some of that too when he asks, what about the ordering? What about, you know, the causal relationships? One question I have is, in many cases, we may not have extensive labeling from the human, but we may have human behavior on that domain doing similar tasks. Do you think that kind of a repository of human behavior
that can
be useful?
Yeah, that can be actually like somehow incorporated to like the human behavior itself. You have human behavior, like human working on her own tasks or her own goals, and then you can use that somehow to like actually assign a score for the plans that you have. Say if it interferes with the robot's plans, then it has some like negative impact on it. So you, in that case, I think you will have to look at like how the plans interfere with each other or the goals interfere with each other if you have like access to say behaviors.
I think the path I was going for is more like, if you have a repository of human behavior and I want to learn a cost function for human, then there could be a relationship to uncover that cost function from the human behavior. Anyway, something we can talk a lot more about. But I think, Rao, you have a comment
So
on
I was just going to add to your question that I think, you know, in terms of learning, it's from the human behaviors. I mean, we looked at that in the beginning. That's so much simpler if you just look at the behavior traces that are stored. The one critical difference tends to be that people sometimes expect something from the robot that's different from what they would be doing themselves. And that is actually the reason why this is a more active way. It's costlier, obviously. So in some sense, I think people actually get spooked if robots behave like people in some cases. I can easily make up such examples. So, but I mean, it's much simpler if you just can depend on stored human behavioral traces. That's just a point to keep in mind.
Yeah, so the difference here is basically it is MRH and not MH. Like MH would be like the model that the human has of her own task, versus MRH is like the mental model of how the robot would actually do that task, whatever task. Yeah, so that's why we have this thing MH, MRH, MR, and MHR, like different types of models.
And my last question is about the end of the talk about the assistive behavior piece. There you have said a few times that one requirement for assistive behavior is for the human to be awareness. I think there is a difference between the human being aware of the assistant behavior the machine has done versus human being aware of the outcome of the assistive behavior. So the human may not necessarily know that the robot helped.
Right.
As long as I can see that my cost is reduced if I choose it, you know, if I go with this path, the assistive behavior has done its work. Right. So just a comment there that it is important to be precise about the language on that requirement. I think your formalization made sense to me. The language was ambiguous.
Okay. Yeah. So I think this actually draws connection to work that Tathagata did on serendipity, planning for serendipity. So there the thing was the robot never comes in front of the human. So but the thing there was he never made sure, I think, that the robot would get assist, like the human would be aware of the assistance that was being provided. But that would be something that comes close to the situation there you said, like the robot is providing the assistance is different from the assistance is being like provided and the human is aware of that assistance, regardless of whether it's robot or somebody else or whatever. Right. Yeah.
Other questions?
So I had a question about, following on the lines of the inputs that you need. Have you thought about what you would actually need to get this thing going? So for instance, if you had a household robot and let's say that COVID is over and you actually have guests at home, right? And some of them are new people, right? They just want to see who the neighbors are now that COVID is gone, right? How do you figure out which of these people you want to share what information with? So and this is for the robot, right? What kind of resources or methods could you draw upon?
Right. So for all of these works, like there was assumption that the robot already knows what to the robot already had access to, like, say, prior information, the sensor models. But if I think the first step would definitely be the robot has to know, like, what are the objectives of these people. Is that something that's part of the scenario you're talking? Are you saying like the robot is aware of these objectives?
No, these are new people, right? So how would you get this thing going in that kind of a scenario?
Okay. So these are new people and you have to predict their preferences. And so I think for that, the robot will have to would need to have some data on like their behavioral traces or something to like actually learn about their preferences, and from that like probably like derive their intentions and then like plan for them. Yeah. So yeah, that would be like way too proactive. Like you don't even know what the task is and you have to like provide assistance.
Right. I mean, you could, you could use the same methods to start getting into dialogues with people and try to.
Right. You can always like do like a more back and forth with them as against like something that you've decided on and you go and you help. Here you can like talk to them and like try to diagnose what is that they want.
Yeah, cool. And nice talk, by the way. I was amazed you were able to fit all of this a ton of work in the short time that you had.
Yeah, I had like a time limit for each section and I was trying to follow that time limit.
Yeah. Good job. Okay, thanks.
So if you remember back in your proposal defense, I asked you a question about the obfuscation. In particular, you had an example where there were a bunch of shipping containers, right?
Right. Yeah.
Right, and you were trying to obfuscate, which container that you were actually, or which containers you were actually shipping out. Right, and my question revolved around to the observer. Not all containers are equal, right? So, you might be shipping out, there might be one container full of rice and another container full of beans, right? And then there's another container full of surface-to-air missiles, right? If you're an aid organization or, a military organization on the other end, you really care about the difference between the missiles and the food items. Or another container full of blankets, right? But the aid organization, may not care about the distinction between the beans and the rice, right? Or and maybe they care about the difference between the blankets and the food items, but less so than they do between the missiles, right, and the food items. And so a lot of my questions that I was writing down here revolve around this central issue that it seems to me that the distance metric here for legibility and for ambiguity needs to take into account what the actual goal is of the observer, namely that they care about the difference between this item and this item, but they don't care about the difference between this item and this item. And the same thing goes for actions, right?
Yeah. Go ahead.
So I'm curious as to, now that you've had 6 months to think about this, right? So what's your answer to this question, and how would you go about incorporating this throughout this work?
So the thing is, in the current K ambiguous or J legible, what I'm saying is I'm just looking at the cardinality of the amount of goals that are there. And like you said, that's not what's important in certain cases. In certain cases, say the likeness of the goals is what is important. And that would probably like be more helpful when you're obfuscating. Like if you're obfuscating say some grains, then you might want to make the human think, the adversary think that these are like different types of grains or something, so that it's uh, more confusing to the adversary. And so what that would involve is basically you would have to have some notion of goal diversity in the formulation itself, and instead of using K ambiguous with respect to just cardinality, you could be like K goal diverse, something like that.
Right. And can you imagine deriving this kind of diversity measure from the actual goals of the agent? You would in some sense have to look at the space of possible things they might do in order to achieve their goals, in order to come up with that diversity measure.
Right. So one thing could be like you could look at say landmarks, like if these goals need to be achieved from some landmark states, and then maybe all the grains have like one type of thing, or in like PDDL things, you could look at like object types or something, and have that kind of like what kind of properties does this goal have, and based on that you can do. But that I think is very like at a syntactic level, but more of something like maybe for grains you have to like put them in the bags and something, so all the grains require bagging versus the blankets require boxing or something. So the things that maybe even the like the actions, what kind of parameters they take, based on that also maybe you can establish some goal diversity measure, but something that basically speaks about the diversity of these different types of goals.
Right. In some sense, you started to do that on the assistive side, right, where you're actually taking into account what the goal is of the observer.
Human.
Yeah. Human. But so now, if you were to carry that over, right, is there an analog to the assistive? So for example, in slide 80, I think it was, right, you've basically got a cost difference here, right, and you're doing a reduction in the human's cost. Is there a direct analog here for the obfuscation case?
Yeah, definitely.
Where you can just talk about an increase in the human's cost, and this minus sign becomes a plus sign over here.
Yeah, so this actually, the MA-COPP setting is quite general in itself. So here I just focused on the assistive side of it, but the general MA-COPP setting can involve multiple different things. Like you can have a collaborative setting where both the human and robot have a goal of their own, and they're working together and reducing the cost of each other's. So basically you will then have this cost differential where you want to reduce, the collaboration should reduce the cost differential for both robot as well as human, versus you will have like some exploitative case where instead of the human's cost being reduced, the robot might be more self-centered agent and is trying to reduce its own cost at the expense of the human. And then you can have like a worse, like scenario where like completely adversarial scenario where the human, where the robot is trying to like increase the cost for the human, like the cost differential after the robot has acted, the cost differential is worse off for the human, and the robot might be even ready to go an extra mile and increase its own cost differential just to make sure that the human suffers an additional cost. So that's like costly punishment, where the robot is ready to go through some cost of its own to increase the cost for the human. So basically you can have like 4 different cases actually in the MA-COPP framework.
Okay.
Yeah, I have a section on this in the conclusion in the thesis. Maybe you can have a look at that.
Okay. Thanks.
Yeah.
Anagha.
Hey, Tony.
Hey, for the sake of time, I think I'm just going to ask one question.
Mm-hmm.
Okay, so so first of all, nice talk. And so my question is really about, like a general question about I think the way that you choose to communicate with humans.
Mm-hmm.
It seems that generally you are choosing implicit behavior to communicate with humans. Now, how do you envision that's being like integrated with active communication? Like, maybe using bioverbal communication.
As well as implicit communication.
Yes.
So yeah, so definitely like implicit communication is useful in like scenarios where it might not be possible for the robot to actually communicate. But say in like more collaborative settings or something, it might also help for the robot to actually just, communicate things explicitly as well. So in this, actually the proactive assistance approach, I don't make too many assumptions on how the robot is actually providing this assistance. So this display of items, so the robot might as well be saying it explicitly, like, okay, I'm doing this, blah, blah, blah. And so these can be some type of capabilities that the robot has. And if it's like that, then it could be like basically these capabilities of, say, speaking, like you can have a speak action which has a epistemic effect on the human to like change the belief update of the human. And so that could be one way where you have like actions like that, and you can incorporate in the current framework itself and like use it.
What about for obfuscation?
Obfuscation. Yeah, so in terms of obfuscation, yeah, you can always be like deceptive, right? You can always be like, look there, and like you do something else. So that could be also a thing where you use it to make the human inattentive, where the epistemic effect of this action is to make the human inattentive in whatever task they are doing while you do something else or something like that. So yeah, definitely has it has importance in even obfuscation side of things.
All right, thank you.
Thank you.
Any other questions in the open session? Going once, going twice, going thrice. In that case, the open session concludes now. So Anagha and the committee will be there. The rest of you, thanks for coming, and stay tuned. We'll find out whether she is a doctor or not soon enough. And thank you for coming. And right now, if you can please leave the Zoom, then we can have the closed session. And okay. I guess now we are done, right? Yeah. Okay, so I'm also going to pause the recording right now. Okay, is she back in? Okay, there she is. Okay. Hi, Anagha.
Hi.
Congratulations.
Thank you.
Congratulations.
Thank you, everyone.
Congratulations.
We're all in implicit communication mode now.
Yeah.
Nothing more from us.
Okay.
Great.
How are you going to celebrate?
No plan.